Subscribe to the channel so you don't miss out on any of these videos. The cosmos is full of mysteries that seem to defy our understanding, but one of the most fascinating involves something deceptively simple: brightness. Imagine for a moment that there's an invisible wall limiting how much light a star or black hole can emit. What if I told you that this limit governs not just the appearance of the brightest objects in the universe but also how they grow, evolve, and interact with the fabric of reality itself? It's called the Eddington limit, and it's one of the most important concepts in astrophysics. But why is there a ceiling on brightness, and what does that tell us about the universe? Stick around, because by the end of this, you'll see stars and black holes in a completely new light. To really understand the Eddington limit, you have to start with a fundamental tug-of-war that defines the universe: the battle between gravity and radiation. On one side, gravity pulls inward, trying to compress matter into denser and denser states. On the other side, radiation pushes outward, carried by the photons streaming from hot, glowing gases. In most cases, gravity wins this battle, shaping planets, stars, and galaxies into stable forms. But when you reach extreme conditions, like the heart of a massive star or the swirling disk of matter around a black hole, this balance becomes far more precarious. Let's break it down. A star shines because of nuclear fusion in its core. This process releases an incredible amount of energy in the form of light and other electromagnetic radiation. The outward push of this radiation balances the inward pull of gravity, keeping the star stable. However, there's a limit to how bright a star can get before the outward pressure of radiation becomes so strong that it blows away the material trying to fall inward. This is the Eddington limit, named after Arthur Eddington, the astrophysicist who first described it in the early 20th century. The Eddington limit isn't just a theoretical boundary, it's a hard stop enforced by physics. When the radiation pressure balances the gravitational pull exactly, we reach the limit. If a star or black hole tries to exceed it by pulling in too much material and shining too brightly, the excess radiation pushes matter away, effectively starving the object of further growth. This delicate balancing act means that the brightest stars and the most voracious black holes are capped in how much they can consume and emit. But here's where it gets even more fascinating. This limit applies not only to stars but also to black holes. Yes, black holes, those infamous cosmic monsters known for devouring anything in their reach. You might think that a black hole, with its seemingly infinite appetite, could consume as much as it wants. But even black holes have rules to follow. When a black hole accretes material, typically gas and dust from a nearby star or interstellar medium, it forms an accretion disk. The friction and heat in this disk cause it to shine brilliantly, often outshining entire galaxies. However, if the black hole tries to consume too much at once, the radiation generated in the accretion disk pushes material away, limiting how much mass the black hole can add to itself. This interplay has profound implications for the universe. It sets an upper bound on the growth of black holes, which, in turn, affects the galaxies they inhabit. Supermassive black holes, the giants lurking at the centers of galaxies, are thought to regulate star formation through this very mechanism. When these black holes approach the Eddington limit, their intense radiation can heat and blow away surrounding gas, halting the birth of new stars. In this way, the Eddington limit acts as a cosmic throttle, shaping the evolution of galaxies over billions of years. The math behind the Eddington limit is surprisingly elegant. It depends on the balance of forces acting on individual particles in the accretion disk or stellar atmosphere. The gravitational force pulling a particle inward is proportional to the object's mass, while the outward force from radiation depends on its luminosity. The formula ties these two forces together, creating a threshold that can be calculated for any object based on its mass and the type of particles in its environment. But the Eddington limit isn't just about numbers. It tells a story about the universe's inherent checks and balances. Without this limit, stars could grow uncontrollably, and black holes could dominate the cosmos, swallowing up everything in sight. Instead, the Eddington limit ensures a kind of cosmic harmony, preventing any one object from becoming too dominant. What's truly mind-blowing is how this limit has been observed in the real universe. Astronomers have spotted black holes and quasars, supermassive black holes emitting enormous amounts of light that seem to hover right at the Eddington limit. Some even appear to momentarily exceed it, a phenomenon that challenges our understanding of the physics involved. Could these objects be breaking the rules, or is there something about the Eddington limit that we don't yet fully grasp? One possibility involves so-called super-Eddington accretion. Under certain conditions, matter might fall onto a black hole faster than the radiation can push it away, temporarily allowing the black hole to exceed the brightness ceiling. Another explanation could involve the geometry of the accretion disk. If the disk isn't uniform, radiation might escape more easily in some directions than others, reducing the effective pressure and allowing for higher luminosity. The Eddington limit also plays a crucial role in understanding the life cycles of stars. For massive stars nearing the end of their lives, crossing the Eddington limit can trigger catastrophic events like supernovae or gamma-ray bursts. These are some of the most energetic phenomena in the universe, scattering elements across space and seeding the formation of new stars and planets. In a way, the Eddington limit isn't just a restriction, it's a trigger for cosmic recycling, ensuring that the universe remains dynamic and ever-changing. And yet, for all we know about the Eddington limit, it remains shrouded in mystery. Why does the universe impose such a limit? Is it a fundamental property of physics, or is it a byproduct of conditions we don't yet understand? As we build more advanced telescopes and study distant stars, quasars, and black holes, we may uncover answers to these questions. For now, the Eddington limit stands as both a rule and a riddle, governing the universe in ways we're only beginning to comprehend. This cosmic ceiling on brightness isn't just an academic curiosity, it has real, observable consequences for the universe's grand architecture. For instance, the Eddington limit determines the pace at which black holes and massive stars grow. Without this natural throttle, these objects might consume matter so rapidly that they disrupt their surroundings to an unimaginable degree. Galaxies could collapse under the gravitational pull of unchecked black holes, or stars might become so luminous that they vaporize their own fuel before they can evolve. The universe as we know it would look completely different. Let's explore the effect of the Eddington limit on stars more deeply. In particularly massive stars, radiation pressure doesn't just balance gravity, it can overpower it. This leads to a phenomenon known as radiation-driven mass loss. These stars essentially shed their outer layers in spectacular stellar winds, ejecting material into space at tremendous speeds. Over time, this process sculpts the star, stripping away its outer shell and exposing its hotter, denser core. Without the Eddington limit acting as a kind of safety valve, these stars might implode prematurely, cutting short their life cycle and disrupting the delicate balance of star formation in the galaxy. Interestingly, the Eddington limit might explain why stars above a certain mass are so rare. Observations show that while small to medium-sized stars like our Sun are common, stars with masses above 100 times that of the Sun are exceedingly rare. The reason is that such massive stars are so luminous that they quickly reach the Eddington limit, ejecting much of their mass before they can grow further. This mass loss also has profound implications for the star's eventual death. A star that sheds much of its outer material might end its life as a neutron star or a less massive black hole, rather than collapsing into a supermassive black hole. Now let's turn back to black holes, where the stakes are even higher. The Eddington limit governs the growth of stellar mass black holes as well as their supermassive cousins at the centers of galaxies. But black holes don't always play by the rules. Some black holes seem to grow far more rapidly than the Eddington limit should allow, especially in the early universe. This has led scientists to propose several intriguing ideas, including the possibility of super-Eddington accretion. In super-Eddington accretion, matter doesn't fall uniformly onto the black hole. Instead, it forms dense, chaotic streams that allow the black hole to swallow material faster than it can radiate energy. The resulting radiation might escape in narrow beams, rather than spreading evenly in all directions. This creates the illusion that the black hole is exceeding the Eddington limit, while in reality, it's finding clever ways to work around it. Observing such phenomena provides valuable clues about the behavior of black holes under extreme conditions. Another fascinating twist involves quasars, which are among the most luminous objects in the universe. Powered by supermassive black holes, quasars emit light that can outshine entire galaxies. Yet even these cosmic lighthouses must contend with the Eddington limit. Quasars are believed to shine at or near this limit, and their behavior offers a unique window into the balance between gravity and radiation. For example, some quasars exhibit variability in their brightness, flickering as they consume matter. These fluctuations might represent the fine-tuned dance of material being pushed and pulled by the competing forces of radiation and gravity. But the story doesn't end there. Observations of quasars and black holes have revealed another layer of complexity: feedback. When a black hole approaches the Eddington limit, the intense radiation it emits doesn't just affect the immediate vicinity. It can influence entire galaxies, heating and expelling gas from the galactic center and halting star formation in the process. This feedback mechanism helps regulate the growth of galaxies, preventing them from becoming too dense or unstable. In this way, the Eddington limit doesn't just govern individual objects, it shapes the evolution of the cosmos on the largest scales. And yet, the Eddington limit is not a one-size-fits-all rule. It depends on the type of matter being accreted and the environment surrounding the object. For example, if a black hole is surrounded by ionized hydrogen, the limit will differ from a situation where it's accreting heavier elements. Similarly, the geometry of the accretion disk, whether it's thick, thin, or warped, can affect how radiation escapes, altering the effective brightness ceiling. These variables make the Eddington limit a flexible yet fundamental law, tailored to the unique circumstances of each cosmic object. What's truly astonishing is how the Eddington limit ties into other mysteries of astrophysics. For instance, it plays a role in the formation of ultraluminous X-ray sources, or ULXs. These enigmatic objects emit X-rays far beyond what would be expected from a typical stellar mass black hole, leading scientists to wonder if they're breaking the Eddington limit or if they represent an entirely new kind of astrophysical phenomenon. The same goes for certain types of neutron stars, which have been observed to emit radiation at levels seemingly beyond the Eddington threshold. Are we witnessing violations of the limit, or do these objects simply operate under conditions we don't yet fully understand? The implications of the Eddington limit extend even to the far reaches of cosmology. It may influence the behavior of the earliest black holes, which formed shortly after the Big Bang. These primordial black holes likely grew rapidly, perhaps aided by super-Eddington accretion, to become the seeds of the supermassive black holes we see today. Understanding how these early black holes interacted with the Eddington limit could provide crucial insights into the formation of galaxies and the large-scale structure of the universe. At its core, the Eddington limit represents a balance, a delicate interplay between two of the universe's most fundamental forces. It's a reminder that even in the most extreme environments, nature imposes boundaries, ensuring that chaos doesn't spiral out of control. And yet, as we've seen, these boundaries aren't always absolute. The exceptions and anomalies surrounding the Eddington limit hint at deeper truths about the cosmos, truths that we're only beginning to uncover. This interplay of forces, where radiation and gravity wrestle for dominance, is one of the most fascinating aspects of the Eddington limit. It showcases the intricate checks and balances that exist in the cosmos, preventing unregulated chaos while allowing for extraordinary phenomena. But as much as the Eddington limit defines cosmic boundaries, it also raises new questions. Why do some black holes and stars seem to skirt this limit? What does it reveal about the physics of extreme environments? To understand these mysteries, scientists must delve even deeper into both observational data and theoretical models. One area of intense interest lies in understanding how black holes defy the Eddington limit in certain conditions. This defiance isn't always a violation of physics, it's often an indication that our models need refinement. For instance, when a black hole accretes matter at super-Eddington rates, it may form thick, toroidal disks of gas that partially trap radiation. This trapped radiation can be funneled out through jets or narrow beams, allowing the black hole to consume matter without radiating at levels that would otherwise blow material away. Such scenarios suggest that the Eddington limit isn't a hard ceiling but rather a flexible boundary influenced by local conditions. This flexibility becomes even more evident when considering different types of stars. For example, hypergiant stars, among the largest and most luminous in the universe, frequently skirt the Eddington limit. These stars undergo episodic outbursts, ejecting massive amounts of material in violent events that temporarily relieve the pressure from radiation. Eta Carinae, a famous hypergiant, is an excellent example of a star that has danced dangerously close to this limit. Its massive outbursts, observed in the 19th century, are believed to have been triggered by radiation pressure exceeding gravitational pull. Such stars live fast and die young, often ending their lives as supernovae or collapsing into black holes. Another area where the Eddington limit plays a pivotal role is in the realm of compact objects, such as neutron stars. These dense remnants of supernova explosions are known for their intense gravitational fields and powerful magnetic fields. When matter accretes onto a neutron star, it can emit X-rays at luminosities near or even exceeding the Eddington limit. In these cases, the intense magnetic fields can channel the inflowing matter into concentrated streams, effectively reducing the surface area over which radiation is emitted. This allows neutron stars to appear super-Eddington while still adhering to the underlying physics. The study of neutron stars and their behavior under the Eddington limit has led to the discovery of pulsating ultraluminous X-ray sources, ULXs. These enigmatic objects emit X-rays at intensities far beyond what traditional models would predict. The key to their extreme luminosities may lie in the interaction between magnetic fields and radiation pressure. As matter spirals onto the neutron star, it creates hotspots that emit intense beams of X-rays. These beams can rotate with the neutron star, creating the pulsating effect observed in ULXs. Such discoveries challenge our understanding of the Eddington limit and demonstrate the importance of magnetic fields in extreme astrophysical environments. Quasars and their supermassive black holes provide another intriguing testbed for the Eddington limit. These cosmic beacons, powered by accretion disks around black holes millions to billions of times the mass of the Sun, emit incredible amounts of energy. Some quasars appear to operate near the Eddington limit for prolonged periods, suggesting that they are finely tuned systems. But not all quasars adhere to this constraint. Observations of certain quasars in the early universe indicate that they grew at astonishing rates, implying that super-Eddington accretion might have been common in the universe's infancy. These findings have profound implications for understanding how supermassive black holes formed and evolved over cosmic time. The influence of the Eddington limit isn't confined to individual objects. It also shapes entire galaxies. In the centers of many galaxies, supermassive black holes regulate their surroundings through a process known as feedback. When these black holes approach the Eddington limit, their intense radiation heats and expels gas from the galactic center. This expulsion halts star formation in the surrounding region, effectively shutting down the galaxy's growth. This feedback mechanism is believed to play a critical role in shaping the size and structure of galaxies, ensuring that they don't grow too large or collapse under their own gravity. Moreover, the Eddington limit has implications for the formation of cosmic structures on even larger scales. In the early universe, black holes and their associated radiation likely influenced the distribution of gas and dark matter, shaping the formation of galaxy clusters. The interplay between radiation pressure and gravitational pull may have created pockets of higher density, where galaxies and clusters eventually formed. Understanding how the Eddington limit operated in these early epochs could provide crucial insights into the large-scale structure of the universe. The Eddington limit also intersects with another cosmic mystery, the phenomenon of dark energy. While the two concepts are distinct, they both highlight the universe's tendency to balance opposing forces. Dark energy, which drives the accelerated expansion of the universe, can be seen as a kind of counterpoint to the Eddington limit. Just as the Eddington limit governs the balance between radiation and gravity on small scales, dark energy governs the balance between gravity and expansion on cosmic scales. Exploring these parallels might offer new perspectives on both phenomena. But despite its significance, the Eddington limit is not the final word on cosmic luminosities. In recent years, observations have uncovered objects that appear to defy this limit, such as superluminous supernovae and certain gamma ray bursts. These events emit energy at levels far exceeding what the Eddington limit would allow for a steady-state system. The key difference is that these are transient phenomena, where the luminosity spikes for a brief period before subsiding. Understanding how such events occur without violating the laws of physics remains an active area of research. In essence, the Eddington limit is both a boundary and an enigma. It provides a framework for understanding the balance of forces in some of the universe's most extreme environments, yet it also invites us to explore the exceptions and anomalies that challenge our understanding. By studying the Eddington limit and its implications, scientists are not only uncovering the secrets of stars and black holes but also gaining insights into the fundamental laws that govern the cosmos. This exploration into the Eddington limit and its cosmic implications continues to reveal how the universe operates on both grand and granular scales. One of the most compelling aspects of the Eddington limit is how it connects seemingly unrelated phenomena across astrophysics, linking the lives of stars, the growth of black holes, and even the evolution of galaxies. But perhaps most intriguingly, it highlights the dynamic tension between creation and destruction that defines the cosmos. To understand this balance, consider how the Eddington limit influences the life cycle of stars. When a star is born, it begins as a dense clump of gas in a molecular cloud. As gravity pulls the gas inward, it heats up, eventually igniting nuclear fusion in its core. This fusion releases energy in the form of light and radiation, counteracting the inward pull of gravity. For most of a star's life, these forces remain in equilibrium, allowing it to shine steadily. However, as a star approaches the end of its life, this delicate balance can falter. Massive stars, in particular, face a dramatic fate. As they exhaust their nuclear fuel, they can no longer sustain the outward pressure needed to counteract gravity. If the star's mass is great enough, it collapses into a neutron star or black hole. Here, the Eddington limit becomes critical, determining how much material these remnants can accrete and how brightly they can shine. In the case of black holes, the Eddington limit plays an especially paradoxical role. On one hand, it restricts how much matter a black hole can consume, preventing runaway growth. On the other hand, the energy emitted as material accretes onto a black hole can have far-reaching effects on its environment. This feedback mechanism can shape the structure of entire galaxies, influencing star formation and gas dynamics. In this way, the Eddington limit doesn't just apply to individual objects, it acts as a regulator of cosmic ecosystems. This regulatory role is evident in phenomena such as active galactic nuclei, AGN. These are regions at the centers of galaxies where supermassive black holes are actively accreting material. The intense radiation emitted by AGN can heat and expel gas from the galaxy's core, slowing or halting star formation. This process, known as AGN feedback, is thought to play a key role in the coevolution of galaxies and their central black holes. Without the Eddington limit, this feedback would likely be much less predictable, leading to a vastly different universe. But as much as the Eddington limit regulates cosmic behavior, it also opens the door to some of the most extreme and puzzling phenomena in astrophysics. Consider ultraluminous X-ray sources, ULXs, which emit far more energy than the Eddington limit would seem to allow. These objects, often associated with neutron stars or stellar mass black holes, challenge our understanding of how matter interacts with radiation. One hypothesis is that their radiation is not emitted isotropically but rather in narrow beams, allowing them to appear super-Eddington from certain perspectives. Similarly, quasars and other high-luminosity objects provide tantalizing clues about the limits of the Eddington framework. Observations of quasars in the early universe suggest that they grew at rates that would require super-Eddington accretion. This raises questions about the physical conditions in the young universe, and whether they allowed for behaviors that are rare or impossible today. For instance, the denser intergalactic medium of the early universe may have enabled more efficient accretion, bypassing some of the constraints imposed by the Eddington limit. In addition to these high-energy phenomena, the Eddington limit also has implications for the formation of massive stars. These stars, which are critical for producing heavy elements and driving galactic evolution, face significant radiation pressure during their formation. Understanding how they accumulate mass without being blown apart by their own radiation remains an open question. Some theories suggest that magnetic fields or turbulent accretion flows may help these stars overcome the Eddington barrier, enabling them to grow to extraordinary sizes. Beyond individual stars and black holes, the Eddington limit also sheds light on broader cosmic processes. For example, it plays a role in the formation of galaxy clusters, the largest gravitationally bound structures in the universe. In these clusters, supermassive black holes and central galaxies can influence the distribution of gas and dark matter through their radiation. This interplay between gravity, radiation, and dark matter shapes the large-scale structure of the cosmos, revealing the interconnected nature of astrophysical phenomena. Yet, for all its explanatory power, the Eddington limit also highlights the limits of our understanding. While it provides a robust framework for predicting the behavior of stars and black holes, it is not a universal law. Instead, it is a guideline that depends on specific conditions, such as the composition of the accreting material and the geometry of the accretion flow. This variability makes the Eddington limit both a powerful tool and a source of ongoing scientific inquiry. One area of active research is the role of magnetic fields in modifying the Eddington limit. In many astrophysical systems, strong magnetic fields can channel accreting material into concentrated streams, reducing the effective area over which radiation is emitted. This can allow objects to exceed the traditional Eddington limit without violating physical laws. Understanding how magnetic fields interact with radiation and gravity is crucial for refining our models of accretion and luminosity. Another intriguing avenue of research involves the interplay between the Eddington limit and relativistic effects. In environments near the event horizons of black holes, where space-time is highly curved, traditional models of radiation pressure and gravity may break down. General relativity predicts that the behavior of light and matter in these extreme conditions could differ significantly from what we observe in less extreme environments. Investigating these relativistic effects could provide new insights into both the Eddington limit and the nature of black holes. The Eddington limit serves as a reminder of the dynamic and ever-changing nature of the cosmos. While it imposes constraints, it also creates opportunities for discovery. By pushing the boundaries of what is possible, stars and black holes operating near the Eddington limit reveal the incredible complexity and diversity of the universe. Each new observation, whether of a super-Eddington object or a novel accretion mechanism, adds another piece to the puzzle, deepening our appreciation of the intricate dance between gravity and radiation. The exploration of the Eddington limit offers a profound glimpse into how the universe balances forces that seem to be in constant opposition. As we delve deeper into its intricacies, we uncover not just the mysteries of stars and black holes, but also the broader principles governing the cosmos. One particularly fascinating aspect of the Eddington limit is how it intersects with the concept of cosmic feedback loops. In these loops, the processes regulated by the Eddington limit influence the very environment that enables them. For instance, a supermassive black hole nearing its Eddington luminosity may emit radiation and winds so powerful that they clear out surrounding gas and dust. This halts further accretion, effectively self-regulating its growth. However, as the black hole's activity subsides, the expelled material may eventually cool and fall back, restarting the cycle. This feedback mechanism underscores the Eddington limit's role as both a constraint and a catalyst for cosmic evolution. But the Eddington limit's significance isn't confined to mature systems like black holes or aging stars. It also plays a pivotal role in the early universe, where conditions were vastly different from those we observe today. Shortly after the Big Bang, the universe was a dense, hot sea of particles and radiation. As structures began to form, the Eddington limit would have dictated how quickly matter could collapse under gravity to form the first stars and galaxies. These, population 3, stars, believed to be the first luminous objects in the universe, were incredibly massive and likely operated close to or even beyond the traditional Eddington limit. Their intense radiation would have shaped their surroundings, influencing the formation of subsequent generations of stars and galaxies. These early stars also raise questions about the role of the Eddington limit in environments with different chemical compositions. Population 3 stars were composed almost entirely of hydrogen and helium, lacking the heavier elements, or metals, found in later generations. This metal deficiency would have affected the opacity of their outer layers and, by extension, the radiation pressure they experienced. Understanding how these early stars balanced radiation and gravity could shed light on the processes that led to the diversity of stars we see today. As we move to more extreme environments, the Eddington limit becomes even more nuanced. Take quasars, for example, some of the most luminous objects in the universe. These active galactic nuclei are powered by supermassive black holes accreting material at astonishing rates. Observations of quasars suggest that many operate near or even above the Eddington limit, raising the question, how do they manage to sustain such high luminosities without being disrupted by their own radiation? One potential explanation involves anisotropic radiation, where the energy emitted is not uniform in all directions. In this scenario, certain regions of the accretion disk or jet may emit far more radiation than others, allowing the system to appear super Eddington without violating the underlying physics. Another possibility is that the accretion process itself may differ from the standard models. For instance, slim disks, a type of accretion disk that becomes optically thick, could allow for higher accretion rates while moderating the effects of radiation pressure. The study of ultraluminous X-ray sources, ULXs, provides additional clues about super Eddington accretion. These mysterious objects, which emit far more X-rays than the Eddington limit would suggest, challenge our understanding of how matter behaves under extreme conditions. Recent research indicates that some ULXs may be powered by neutron stars with strong magnetic fields, which can funnel accreting material into narrow streams. This focused accretion reduces the effective area over which radiation pressure acts, allowing these objects to exceed the traditional Eddington limit. The interplay between magnetic fields and the Eddington limit also has implications for gamma-ray bursts, GRBs, some of the most energetic events in the universe. These bursts, thought to result from the collapse of massive stars or the merger of compact objects, involve the rapid release of energy in the form of gamma rays. The extreme luminosities of GRBs suggest that they operate in regimes where the traditional Eddington limit no longer applies. Investigating these events could provide valuable insights into how radiation and matter interact under the most extreme conditions imaginable. On a larger scale, the Eddington limit influences the growth and evolution of galaxies. As supermassive black holes accrete material and emit energy, they can heat and expel gas from their host galaxies, suppressing star formation. This process, known as quasar or AGN feedback, is thought to be a key factor in regulating the size and structure of galaxies. Without the Eddington limit, this feedback would likely be far less predictable, potentially leading to a very different universe. Interestingly, the Eddington limit also has potential implications for dark matter and dark energy, two of the most mysterious components of the universe. While these phenomena are not directly influenced by radiation pressure, the processes regulated by the Eddington limit could affect the distribution and behavior of visible matter, indirectly influencing the overall dynamics of the cosmos. For instance, the outflows driven by AGN feedback could alter the distribution of dark matter in galaxy clusters, providing clues about its nature. Despite its central role in astrophysics, the Eddington limit is not a fixed boundary. It depends on various factors, including the composition and geometry of the accreting material, the strength of magnetic fields, and the relativistic effects near compact objects. These variables make the Eddington limit a dynamic and adaptable framework, capable of accommodating a wide range of astrophysical phenomena. As we continue to study the Eddington limit, we are reminded of the interconnectedness of the universe. From the smallest stars to the largest black holes, the balance between radiation and gravity shapes the cosmos in profound ways. Each new discovery, whether of a super Eddington object or a novel accretion mechanism, deepens our understanding of this delicate equilibrium. Yet, for all its explanatory power, the Eddington limit also highlights the limits of our knowledge. It serves as both a tool for understanding and a challenge for exploration, inviting us to probe the boundaries of what is possible in the universe. By studying the Eddington limit and its implications, We not only learn more about the cosmos but also gain a deeper appreciation for the intricate dance of forces that governs its behavior. The implications of the Eddington limit extend far beyond theoretical astrophysics. They touch on fundamental questions about the universe's origins, its evolution, and even its ultimate fate. The balance between radiation and gravity, so precisely defined in this context, mirrors a broader theme in cosmology: the tension between opposing forces shaping the cosmos. One of the most intriguing areas where the Eddington limit plays a subtle yet pivotal role is in the study of galaxy clusters, the largest gravitationally bound structures in the universe. At the heart of many galaxy clusters lies a supermassive black hole, often feeding on the surrounding material. These central black holes, through their accretion-driven energy output, can regulate the thermal state of the intracluster medium, the vast reservoirs of hot gas permeating the cluster. The energy released as these black holes approach the Eddington limit can prevent gas from cooling too rapidly, thus delaying or even halting star formation on a massive scale. This regulation links the small-scale physics of black holes with the large-scale evolution of galaxies and clusters, showcasing the interconnected nature of cosmic processes. Moreover, the Eddington limit has profound implications for the mysterious process of reionization. Following the cosmic dark ages, the first stars and galaxies began emitting ultraviolet light, reionizing the neutral hydrogen that filled the universe. The rate at which this reionization occurred depended heavily on how efficiently these early objects could convert matter into energy, a process directly influenced by the Eddington limit. If early stars or black holes consistently exceeded the Eddington limit, their intense radiation could have accelerated reionization, altering the timeline of cosmic history. The Eddington limit also serves as a tool for understanding the enigmatic nature of black hole mergers, as observed through gravitational waves. When two black holes collide, the resulting single black hole often experiences a phase of rapid growth, consuming material at extraordinary rates. The question of whether these newly formed black holes temporarily surpass the Eddington limit is critical for understanding the post-merger environment. Observing and modeling these events helps refine our understanding of how the universe recycles and redistributes its energy. But perhaps one of the most profound ways the Eddington limit influences our understanding of the universe is through its relationship with time scales. The rate at which matter can be accreted by black holes and stars, governed by the Eddington limit, sets a natural clock for various cosmic events. For instance, the growth of supermassive black holes, the evolution of quasars, and even the lifespans of stars are all tied to the interplay between radiation pressure and gravity. By studying these time scales, astronomers can piece together the chronology of the universe, reconstructing events that occurred billions of years ago. In addition to these grand cosmic narratives, the Eddington limit has implications for more localized phenomena. For example, the concept is crucial in understanding how binary star systems evolve. In systems where one star is a compact object like a white dwarf, neutron star, or black hole, the Eddington limit dictates how quickly the companion star can lose mass to its dense neighbor. This process, known as Roche-Lobe overflow, can lead to phenomena such as X-ray binaries, type Ia supernovae, and even the formation of millisecond pulsars. Each of these outcomes provides a different window into the physics of extreme environments, showcasing the versatility of the Eddington framework. The study of the Eddington limit also offers a glimpse into the future of astrophysics. As observational technologies improve, researchers are increasingly able to detect objects that push or even break the traditional boundaries of this limit. For instance, instruments like the Event Horizon Telescope allow scientists to peer directly into the environments surrounding supermassive black holes, where deviations from the Eddington limit may reveal new physics. Similarly, upcoming missions like the James Webb Space Telescope and the Extremely Large Telescope will provide unprecedented views of the early universe, shedding light on how the first stars and galaxies navigated the constraints imposed by radiation pressure. Furthermore, the theoretical understanding of the Eddington limit continues to evolve. Advances in computational astrophysics are enabling researchers to simulate the complex interplay between radiation, gravity, and magnetic fields in extreme environments. These simulations are uncovering scenarios where the traditional Eddington framework may break down, such as in highly magnetized accretion disks or in regions dominated by relativistic effects. By pushing the limits of our models, scientists are not only refining the Eddington concept but also discovering new phenomena that challenge our understanding of the universe. Even as we deepen our understanding, the Eddington limit remains a source of mystery. For instance, how does it apply in environments with exotic states of matter, such as quark-gluon plasma or the interiors of neutron stars? What happens when quantum effects become significant, as in the immediate vicinity of black holes? These questions highlight the frontiers of astrophysics, where the interplay between radiation and gravity intersects with the fundamental laws of nature. The Eddington limit also raises philosophical questions about the nature of balance and regulation in the universe. Why does such a limit exist in the first place? Is it a coincidence, or does it reflect a deeper principle underlying the cosmos? These questions remind us that science is not just about discovering facts but also about seeking meaning in the patterns we observe. Ultimately, the Eddington limit serves as a testament to the universe's capacity for balance amidst chaos. Whether regulating the growth of black holes, shaping the evolution of galaxies, or influencing the earliest moments of cosmic history, this seemingly simple concept encapsulates some of the most profound mysteries of existence. By studying the Eddington limit, we not only uncover the mechanisms that govern the cosmos but also gain a deeper appreciation for the intricate dance of forces that make our universe possible. As we delve even deeper into the significance of the Eddington limit, it becomes evident that this concept acts as a universal checkpoint, one that nature itself respects to maintain cosmic order. The balance it represents, between the outward push of radiation and the inward pull of gravity, underscores how delicately calibrated the universe is. This calibration is not just an abstract principle, it manifests in nearly every observable corner of the cosmos. Consider the formation and evolution of quasars, the immensely bright and energetic centers of some galaxies powered by supermassive black holes. Quasars often shine with luminosities that rival or even surpass entire galaxies. This incredible brightness comes from matter spiraling into the black hole at the center, forming an accretion disk that emits vast amounts of energy as it heats up. However, this process is intrinsically limited by the Eddington threshold. If the black hole's accretion rate surpasses the Eddington limit, the intense radiation pressure can blow away the surrounding matter, effectively throttling further growth. The regulation provided by the Eddington limit explains why quasars don't grow unchecked. Without this natural ceiling, supermassive black holes could theoretically consume all nearby material, leading to much darker, less dynamic galaxies. Instead, the interplay between radiation and gravity ensures that galaxies remain active and vibrant, fostering environments where stars can form and planetary systems, potential cradles of life, can emerge. Yet nature is never entirely straightforward. In some extreme cases, black holes appear to challenge the Eddington limit. These super Eddington accretion scenarios are of significant interest to astrophysicists. In these cases, matter seems to flow into the black hole at rates higher than the Eddington limit would predict, potentially due to the effects of magnetic fields or the chaotic dynamics of the accretion disk. These phenomena not only push the boundaries of our understanding but also raise critical questions about whether the Eddington limit is truly an unbreakable rule or simply a guideline that can be circumvented under specific conditions. Another realm where the Eddington limit proves crucial is in the context of stellar evolution. Massive stars, particularly those in their later stages, often push close to their Eddington luminosity. As they burn through their nuclear fuel, these stars become more luminous, and the outward radiation pressure grows stronger. When a star approaches the Eddington limit, its outer layers can become unstable, leading to massive stellar winds or even partial ejections of its outer envelope. These processes contribute to the enrichment of the interstellar medium with heavier elements, seeding future generations of stars and planets. For stars at the extreme end of the mass spectrum, the Eddington limit can spell the difference between life and death. When a star exceeds a certain mass, often referred to as the Eddington mass threshold, the intense radiation pressure can prevent the star from forming altogether. This theoretical upper limit on stellar mass explains why we don't see stars much larger than 150 to 200 times the mass of our Sun, despite the universe's apparent ability to gather more material in certain regions. The Eddington limit also provides a framework for understanding the enigmatic nature of gamma-ray bursts, GRBs, some of the most energetic explosions in the universe. Long-duration GRBs, in particular, are thought to result from the collapse of massive stars into black holes. During this process, the star releases an enormous amount of energy, much of which escapes in the form of radiation. The behavior of this radiation, its intensity, directionality, and impact on surrounding matter, can often be modeled using the principles underlying the Eddington limit. This connection helps astrophysicists make sense of these rare but profoundly impactful cosmic events. The Eddington limit doesn't just regulate how stars live, it also governs how they die. When stars reach the end of their lives, their ability to maintain equilibrium often depends on the balance between radiation and gravity. For stars that become white dwarfs, neutron stars, or black holes, the Eddington limit continues to play a role in their interactions with surrounding material. White dwarfs, for instance, can accrete material from a binary companion, leading to nova explosions or even a catastrophic Type I supernova. In these scenarios, the Eddington limit helps determine the accretion rate and, by extension, the timing and intensity of these events. Meanwhile, in neutron stars, the extreme density and intense magnetic fields create environments where the traditional Eddington limit may no longer apply in the same way. Observations of X-ray bursts from neutron stars suggest that in some cases, the effective luminosity can exceed the Eddington limit, a phenomenon that challenges our theoretical models. These super-Eddington bursts provide a unique laboratory for studying the behavior of matter and radiation under conditions far beyond anything achievable on Earth. Looking to the future, the Eddington limit will remain a cornerstone of astrophysical research, especially as new technologies allow us to observe the universe with greater precision. Projects like the Laser Interferometer Space Antenna, LISA, will enable scientists to detect gravitational waves from the mergers of black holes and other massive objects, events where the Eddington limit's effects on accretion and energy emission are likely to be evident. Similarly, upcoming telescopes like the Nancy Grace Roman Space Telescope will provide deeper insights into the early universe, where the interplay between radiation and gravity shaped the formation of the first galaxies and black holes. As we continue to push the boundaries of our understanding, the Eddington limit serves as both a guidepost and a challenge. It reminds us that even the most extreme phenomena in the universe are governed by principles that can be understood and modeled. At the same time, it invites us to explore the exceptions, the edge cases, and the scenarios where nature seems to rewrite its own rules. Ultimately, the Eddington limit is more than just a concept in astrophysics. It's a window into the profound elegance of the universe. It encapsulates the delicate balance between creation and destruction, between chaos and order. By studying it, we not only learn about the forces that shape stars, black holes, and galaxies but also gain a deeper appreciation for the intricate web of relationships that underpins all of existence. The Eddington limit is more than a constraint, it's a testament to the remarkable balance found in cosmic processes. To fully grasp its implications, we must dive further into how it regulates the growth of black holes, influences star formation, and governs the dynamics of galaxies across time. Let's explore black holes in more detail, especially the ones that challenge the Eddington limit. These supermassive entities, lurking at the centers of galaxies, are the engines behind quasars and active galactic nuclei (AGN). At their peak activity, black holes accrete matter at astounding rates, generating enormous luminosities. As they approach the Eddington limit, the radiation pressure from the accretion disk pushes back against the inflowing gas, creating a feedback loop. This mechanism prevents the black hole from consuming its surroundings too quickly, ensuring a steady growth process over millions of years. However, observations suggest that some black holes seem to defy this balance. Super-Eddington accretion rates have been inferred in a handful of cases, particularly during the early universe. These black holes, formed less than 1 billion years after the Big Bang, appear to have grown to billions of solar masses in a short span of cosmic time. This rapid growth poses a mystery. How could these black holes have accreted matter so quickly without being halted by the Eddington limit? One explanation lies in the geometry of the accretion flow. If the infalling matter forms a dense, narrow disk rather than a spherically symmetric cloud, radiation can escape more easily along the poles, allowing higher accretion rates along the disk's plane. Another intriguing phenomenon tied to the Eddington limit is the existence of ultraluminous X-ray sources, ULXs. These objects emit X-rays at luminosities exceeding the Eddington limit for a typical stellar mass black hole. ULXs are thought to be either stellar mass black holes accreting matter at super-Eddington rates or intermediate mass black holes whose larger masses shift the Eddington threshold to higher luminosities. Either scenario challenges our understanding of how matter behaves under extreme gravitational and radiative forces. Beyond black holes, the Eddington limit plays a vital role in star formation. Stars form from collapsing clouds of gas and dust within molecular clouds. During the collapse, the growing protostar heats up and begins emitting radiation. If the protostar's luminosity approaches the Eddington limit, the radiation pressure can counteract the gravitational collapse, slowing or even halting the inflow of material. This feedback mechanism helps regulate the maximum mass a star can achieve during its formation phase. Massive stars, particularly those that form in dense star clusters, are especially influenced by this limit. As their luminosity increases with mass, the Eddington limit imposes a natural cap on their growth. Without this constraint, stars could grow to much larger sizes, disrupting the delicate balance of stellar populations and galaxies. The limit also explains why stars more massive than a few hundred solar masses are exceedingly rare, as the radiation pressure becomes overwhelming at those scales. For stars in their later stages, the Eddington limit governs phenomena like stellar winds and mass loss. In the case of luminous blue variables, LBVs, a class of massive stars nearing the end of their lives, the intense radiation pressure can drive powerful outflows, shedding significant portions of the star's mass. These mass loss events shape the star's evolution and can lead to spectacular explosions, such as supernovae or even parinstability supernovae, where the entire star is obliterated without leaving behind a black hole or neutron star. The Eddington limit's effects extend to galaxies as well. At the heart of most galaxies lies a supermassive black hole, whose activity is closely linked to the galaxy's evolution. The growth of the black hole and the formation of stars in the surrounding galactic disk are regulated by feedback processes influenced by the Eddington limit. When the black hole's accretion rate approaches the limit, the resulting radiation and outflows can heat and expel gas from the galaxy, suppressing further star formation. This interplay helps explain the observed correlation between black hole mass and the properties of their host galaxies, such as the bulge mass and stellar velocity dispersion. The Eddington limit also sheds light on phenomena like galactic winds and feedback in galaxy clusters. During periods of intense activity, such as starbursts or AGN phases, the combined radiation pressure from stars and accreting black holes can drive large-scale outflows of gas. These galactic winds influence the distribution of matter in the universe, enriching the intergalactic medium with heavy elements, and regulating the growth of galaxies over cosmic time. In extreme cases, the Eddington limit might even influence the behavior of exotic objects like magnetars, neutron stars with incredibly strong magnetic fields. Magnetars emit bursts of X-rays and gamma rays that, in some instances, appear to exceed the Eddington luminosity. These bursts challenge our understanding of the interplay between radiation, magnetic fields, and matter under extreme conditions, pushing the boundaries of theoretical astrophysics. The theoretical framework of the Eddington limit is not without its complexities. While it provides a robust model for understanding radiation pressure and gravitational balance, real-world systems often exhibit deviations from the idealized conditions assumed in its derivation. Factors like magnetic fields, non-spherical geometries, and relativistic effects can modify the behavior of accreting systems, leading to scenarios where the Eddington limit appears to be violated. These deviations are not failures of the theory but rather opportunities to refine our models and deepen our understanding of the universe. As we continue to study the Eddington limit, new questions arise. How does the limit evolve under the influence of dark matter and dark energy? Could alternative theories of gravity alter the balance between radiation pressure and gravitational pull? These questions underscore the dynamic nature of astrophysical research, where each discovery opens new avenues of inquiry. The Eddington limit stands as a cornerstone of our understanding of the cosmos, bridging the microcosm of individual stars and black holes with the macrocosm of galaxies and the universe itself. It encapsulates the intricate dance of forces that govern the behavior of matter and energy on the grandest scales. By studying this limit, we uncover not only the mechanics of cosmic objects but also the underlying principles that make our universe both comprehensible and profoundly mysterious. The implications of the Eddington limit extend even further when we consider its role in shaping the large-scale structure of the universe. As we venture into the early epochs of cosmic history, the interplay between the Eddington limit and accretion processes becomes pivotal in understanding the formation of some of the most energetic and enigmatic phenomena in the cosmos. During the infancy of the universe, the first stars and black holes formed in an environment vastly different from the present day. These primordial objects, often referred to as population 3 stars, were composed almost entirely of hydrogen and helium. Unlike their successors, these stars faced minimal metal enrichment, allowing them to reach immense masses before their radiation pressure approached the Eddington limit. When these massive stars ended their lives, they likely seeded the formation of the first black holes, which would later grow into the supermassive black holes we observe at the centers of galaxies. The accretion history of these early black holes offers insight into how the Eddington limit governs cosmic evolution. In the dense and gas-rich environment of the early universe, black holes could accrete matter rapidly, potentially nearing or even temporarily exceeding the Eddington limit. Such phases of super-Eddington accretion could help explain the existence of quasars observed less than a billion years after the Big Bang. These luminous objects, powered by supermassive black holes, challenge our understanding of how black holes grow so quickly under the constraints imposed by the Eddington limit. One possible explanation for these early black holes lies in anisotropic radiation. In certain conditions, the radiation from the accretion disk may escape preferentially along specific directions, creating radiation channels. These channels allow for higher accretion rates along other paths, effectively bypassing the Eddington limit in localized regions without violating the fundamental principles of physics. Such processes would have been particularly relevant during the early stages of galaxy formation when gas was abundant, and black hole growth was unconstrained by the scarcity of surrounding matter. In modern galaxies, the Eddington limit remains a critical factor in regulating the relationship between central black holes and their host galaxies. Observations reveal a remarkable correlation between the mass of a galaxy's central supermassive black hole and the velocity dispersion of stars in the galactic bulge. This relationship, known as the M-sigma relation, suggests a deep connection between black hole growth and galaxy evolution. The Eddington limit plays a central role in this feedback process, as radiation-driven outflows from active black holes can influence the distribution and dynamics of gas within galaxies. These outflows, driven by radiation pressure near the Eddington limit, can trigger or suppress star formation depending on their intensity. In some cases, the outflows expel gas from the galactic nucleus, depriving the region of the raw material needed for star formation. This process, known as quenching, is thought to contribute to the transition of galaxies from star-forming to quiescent states. Conversely, in other cases, the same outflows can compress surrounding gas clouds, triggering new waves of star formation. The dual nature of these feedback mechanisms highlights the complexity of the Eddington limit's influence on cosmic structures. Beyond individual galaxies, the Eddington limit also has implications for galaxy clusters and the intergalactic medium. In massive clusters, the combined radiation from active galactic nuclei, AGN, and star formation processes can create large-scale effects, such as heating the intracluster medium and driving outflows that shape the cluster's evolution. These processes are crucial for understanding phenomena like the Sunyaev-Zeldovich effect, where radiation interacts with the hot gas in galaxy clusters, providing a window into the large-scale structure of the universe. On a more theoretical level, the Eddington limit raises profound questions about the nature of accretion and radiation processes in extreme environments. In the vicinity of black holes, relativistic effects come into play, modifying the balance between gravitational pull and radiation pressure. General relativity predicts that the curvature of spacetime near a black hole can bend the path of escaping radiation, altering its pressure and allowing for more complex accretion dynamics. These relativistic effects become particularly pronounced near the event horizon of a black hole, where the gravitational pull is at its strongest. Magnetic fields add another layer of complexity to the Eddington limit. In many astrophysical systems, strong magnetic fields can channel accreting matter along field lines, creating jets and collimated outflows. These magnetic interactions can change how radiation escapes from the system, modifying the effective Eddington limit. For example, in systems like pulsars or magnetars, the interplay between radiation pressure, magnetic fields, and gravitational forces creates highly anisotropic emission patterns, challenging our understanding of how these objects maintain equilibrium. The role of the Eddington limit in the universe is not limited to observable phenomena. It also intersects with some of the most fundamental questions in cosmology, such as the nature of dark matter and dark energy. While these components of the universe do not interact directly with electromagnetic radiation, they influence the distribution of ordinary matter and the formation of structures that obey the Eddington limit. For instance, the presence of dark matter in galactic halos affects the availability of gas for accretion onto black holes, indirectly shaping the conditions under which the Eddington limit applies. Dark energy, responsible for the accelerated expansion of the universe, may also play a subtle role in the behavior of systems governed by the Eddington limit. As the universe expands, the density of matter decreases, altering the environment in which stars and black holes evolve. Over cosmic timescales, these changes could shift the balance between gravitational pull and radiation pressure, influencing the long-term growth of black holes and the fate of luminous objects in the cosmos. The Eddington limit is, in many ways, a bridge between the observable universe and the theoretical principles that govern it. Its relevance spans scales from individual stars and black holes to entire galaxies and clusters, making it a cornerstone of astrophysical understanding. By studying this limit, we not only gain insights into the behavior of extreme objects, but also uncover the underlying symmetries and balances that define our universe. As we delve deeper into the intricacies of the Eddington limit, it's important to recognize its role as a dynamic threshold rather than a fixed boundary. The conditions surrounding stars and black holes often create environments where the Eddington limit is pushed, bent, or momentarily exceeded. These phenomena reveal just how nuanced and complex the universe's mechanisms are. One fascinating aspect of this is the concept of super-Eddington accretion. While the Eddington limit is theoretically a ceiling, there are astrophysical situations where objects appear to defy it, albeit temporarily or under special conditions. For instance, certain accretion disks, vast structures of swirling matter around black holes or neutron stars, can achieve configurations that allow matter to flow inward at rates exceeding the Eddington limit. This phenomenon often involves geometric beaming, where radiation is funneled in specific directions rather than radiating isotropically. By focusing the energy output into narrow beams, these systems create pathways for additional accretion without blowing themselves apart. Super-Eddington accretion is particularly relevant in understanding ultraluminous X-ray sources, ULXs. These enigmatic objects emit X-rays at intensities that seem impossible under the constraints of the Eddington limit. For decades, astrophysicists debated whether ULXs were small black holes accreting at super-Eddington rates, or entirely different types of systems, such as intermediate-mass black holes. The discovery of pulsars within some ULXs added another layer of intrigue, as pulsars, rotating neutron stars with intense magnetic fields, were not traditionally expected to achieve such luminosities. The interplay between radiation pressure, magnetic fields, and accretion geometry in these systems continues to challenge and refine our understanding of the Eddington limit. Similarly, the concept of photon bubbles offers another potential mechanism for exceeding the Eddington limit. In certain highly luminous environments, the intense radiation creates pockets of lower density gas, forming bubbles that allow photons to escape more efficiently. These bubbles reduce the overall radiation pressure, enabling the system to accrete more matter than would otherwise be possible under standard Eddington constraints. This phenomenon may play a role in the extreme luminosities observed in some accreting neutron stars and black holes. Beyond accretion disks, the Eddington limit also interacts with stellar evolution in unexpected ways. For example, during the later stages of a massive star's life, intense radiation pressure from the core can exceed the gravitational pull of the outer layers. This imbalance can trigger massive stellar winds, ejecting material into space and significantly altering the star's mass and future evolution. In some cases, these winds can lead to the formation of Wolf-Rayet stars, hot, luminous objects that have shed their outer hydrogen layers, exposing their helium-rich cores. These stars, operating near or above the Eddington limit, are among the most dramatic examples of how radiation pressure shapes stellar life cycles. The Eddington limit also has profound implications for understanding gamma-ray bursts, GRBs, the universe's most powerful explosions. GRBs are thought to originate from the collapse of massive stars or the merger of neutron stars, producing jets of radiation and particles that are extraordinarily luminous. The processes governing these jets must navigate the constraints of the Eddington limit, while also accommodating the relativistic effects of near-light-speed motion. The balance between radiation pressure and gravitational forces in these extreme environments offers valuable insights into how nature achieves such staggering energy outputs. Another intriguing frontier involves the role of the Eddington limit in tidal disruption events, TDs. These occur when a star ventures too close to a supermassive black hole and is torn apart by tidal forces. The debris from the star forms an accretion disk around the black hole, emitting intense radiation as it spirals inward. Observations of TDs often show luminosities near or exceeding the Eddington limit, providing a unique laboratory for studying how radiation pressure interacts with chaotic, rapidly changing environments. In addition to its astrophysical implications, the Eddington limit raises fascinating philosophical and theoretical questions. At its core, the limit represents a balance, a point of equilibrium between opposing forces. This balance is a recurring theme in nature, appearing in everything from atomic structures to ecological systems. The Eddington limit exemplifies how the universe often operates at the edge of stability, with competing forces finding harmony in ways that allow complexity and diversity to flourish. On a theoretical level, the Eddington limit also intersects with questions about the fundamental nature of gravity and light. For instance, alternative theories of gravity, such as modified Newtonian dynamics, MOND, or extensions of general relativity, could potentially alter the conditions under which the Eddington limit applies. Similarly, advances in quantum gravity, an as yet untested theory that seeks to unify general relativity with quantum mechanics, might reveal new insights into how radiation pressure and gravitational forces interact at the smallest scales. The Eddington limit also inspires new questions in the field of computational astrophysics. Simulating environments where the Eddington limit is approached or exceeded requires sophisticated models that account for a wide range of physical processes, including radiation transport, magnetic fields, and relativistic effects. These simulations are essential for interpreting observations and testing hypotheses, yet they also highlight the limitations of our current understanding. Every time we push the boundaries of what we can model, we uncover new complexities and challenges, driving the field forward. Ultimately, the Eddington limit is more than just a mathematical expression or a physical boundary. It is a window into the dynamic and interconnected nature of the cosmos. From the smallest neutron stars to the largest galaxies, the principles underlying the Eddington limit shape the evolution and behavior of countless objects. By studying this limit, we not only deepen our understanding of astrophysics but also connect with the broader narrative of the universe, one of balance, adaptation, and the constant interplay of forces. As we continue exploring the vast implications of the Eddington limit, it's essential to emphasize that this boundary isn't merely a static number etched in the cosmic fabric. It's a concept that continuously reshapes how we think about the universe. The more we understand it, the more we realize how intricately intertwined the forces of gravity and radiation are in determining the destiny of stars and black holes. This relationship is critical for explaining the evolution of massive stars, the formation of exotic objects like black holes, and the behavior of some of the most luminous phenomena in the universe. Consider, for instance, the death of a star. The Eddington limit plays a pivotal role in determining the fate of stars nearing the end of their lifespans. In the final stages of stellar evolution, the star's core may begin to collapse under its own gravity, while the outer layers are pushed outward by the intense radiation pressure from the core. When this balance shifts, the outer layers may be ejected in powerful stellar winds. These winds not only contribute to the formation of nebulae and interstellar dust but also regulate the amount of mass that the star sheds before ultimately collapsing into a white dwarf, neutron star, or black hole. In massive stars, where radiation pressure becomes especially significant, the Eddington limit can help determine whether the star dies in a spectacular supernova explosion or undergoes direct collapse into a black hole. This process is further influenced by the star's environment. In a dense star cluster, for example, where stars are closely packed together, the influence of surrounding objects can alter the way radiation pressure interacts with gravitational forces. These interactions can lead to what is known as supernovae precursors, or stars that undergo violent instability due to the intense radiation pressure from nearby companions. In these environments, the traditional understanding of the Eddington limit is expanded, as it becomes less about the individual properties of a star and more about the complex interactions within a star system. Supernovae, which are often seen as a star's ultimate explosion, represent another arena where the Eddington limit plays a critical role. A supernova is triggered when a massive star's core collapses under its own gravity, and the shockwaves from this collapse send a vast amount of energy and material into space. However, this process is also influenced by radiation pressure, which in turn regulates the dynamics of the explosion. As the star reaches its final stages, radiation pressure can cause a delay in the collapse, creating complex dynamics between the forces of gravity, radiation, and the materials surrounding the core. The details of this process are still an area of active research, with new models constantly being developed to better understand how the Eddington limit shapes the behavior of these extreme cosmic events. On an even more extreme scale, the supermassive black holes at the centers of galaxies present some of the most fascinating examples of the Eddington limit in action. These massive objects, which can have masses millions or even billions of times that of the Sun, exert an incredible gravitational pull. However, their power is balanced by the intense radiation produced from the matter being consumed in their accretion disks. The Eddington limit helps explain why black holes of this size do not continue to grow uncontrollably, as the radiation pressure they generate ultimately pushes against the inflowing material. Interestingly, even supermassive black holes don't always follow the strict constraints of the Eddington limit. In some galaxies, active galactic nuclei, AGNs, emit more radiation than would be expected given the mass of their central black holes. This excess radiation is thought to arise from the complex dynamics of the accretion disk and the relativistic jets ejected from the poles of the black hole. In these cases, the relationship between the radiation pressure and gravitational forces is not so much a straightforward balance, but a constantly evolving and often chaotic dance of energy and matter. In addition to the extremes observed in astrophysical systems, the Eddington limit also ties into the broader concept of cosmic evolution. When considering how galaxies form and evolve, the role of radiation pressure and accretion is crucial. In the early universe, the radiation from forming stars and black holes would have contributed to the heating and ionization of the surrounding gas, impacting the formation of galaxies. In fact, some models suggest that radiation pressure from the first generations of stars may have regulated the rate at which galaxies could grow by influencing the gas cooling processes that are essential for star formation. The Eddington limit also provides a key insight into the formation of the first black holes. Early in the history of the universe, when the first massive stars were forming, the conditions were ripe for the creation of black holes with masses far beyond what we observe today. However, the interplay between radiation and gravity would have constrained how much matter these early black holes could accrete. The Eddington limit thus not only provides us with a tool to understand black hole growth but also gives us clues about the conditions in the early universe that allowed these objects to form. As we continue to probe these distant, extreme environments, Technological advances in observational astronomy provide us with increasingly detailed pictures of how the Eddington limit plays out in practice. The launch of powerful space telescopes like the James Webb Space Telescope and the continued refinement of ground-based observatories like the Event Horizon Telescope promise to reveal new details about how radiation pressure and gravity interact in black holes and other extreme objects. These observations will enable us to better understand how the Eddington limit regulates the growth of supermassive black holes, the behavior of accretion disks, and the formation of stars and galaxies. One of the most exciting developments in modern astrophysics is the way that we can now study these phenomena in real time. Gravitational wave astronomy, which involves detecting the ripples in space-time caused by massive objects like black holes and neutron stars colliding, has opened up an entirely new way of observing the universe. As we collect more data from gravitational wave detectors, we can study the dynamics of black hole mergers and other extreme events that involve radiation pressure and gravitational collapse. These observations give us a direct window into the environments where the Eddington limit is operating, allowing us to test our theoretical models and explore the nuances of how this fundamental boundary impacts the evolution of the universe. The study of the Eddington limit is far from over. In fact, it is only by continuing to explore the edge of this boundary that we will unlock even greater mysteries about how stars, black holes, and galaxies evolve. As we push the limits of what we know, we will likely encounter new phenomena and questions that challenge our understanding of the universe. Whether it's through new discoveries in supernovae, black holes, or even in the farthest reaches of the cosmos, the Eddington limit remains an essential part of the cosmic story. As we continue to peel back the layers of the Eddington limit, it becomes clear that this boundary is not just a static rule, it's a dynamic principle that influences the formation and behavior of objects on every scale. From the birth of the first stars to the formation of supermassive black holes at the centers of galaxies, the Eddington limit offers us insight into some of the universe's most fundamental processes. It's a concept that transcends simple equations and reaches into the very heart of astrophysical evolution. Let's zoom out for a moment and take a broader perspective. The Eddington limit has profound implications for the large-scale structure of the universe. It's one of the mechanisms that regulates how much material can be funneled into the deepest gravitational wells. Whether we're talking about the formation of stars, the evolution of black holes, or the creation of galaxies, radiation pressure plays a pivotal role in shaping the cosmos. The way that galaxies grow and how stars form within them is intricately linked to the interplay between gravity and radiation, governed by the Eddington limit. This is particularly important when we consider the concept of starburst galaxies, which are galaxies undergoing a period of extremely rapid star formation. In these environments, the intense radiation from newly formed stars pushes outward against the surrounding gas, preventing it from collapsing to form even more stars. Here, the Eddington limit helps us understand why some galaxies seem to undergo bursts of rapid growth, and then reach a plateau, unable to sustain further expansion. In these starburst galaxies, the radiation pressure from the intense stellar wind reaches a point where it begins to slow down or halt further star formation, creating an interesting balance between creation and destruction. Now, if we pivot back to black holes, there's a fascinating relationship between the Eddington limit and what is known as the quasar phase of a black hole's life. A quasar is essentially a supermassive black hole actively pulling in matter, surrounded by a glowing accretion disk of hot gas that emits immense radiation. For a long time, quasars were considered to be among the brightest objects in the universe. But the Eddington limit provides a fascinating explanation for this brightness. It tells us that there is a maximum rate at which a black hole can accrete material before radiation pressure from the accretion disk essentially halts further infall. At the heart of quasars is an intense struggle between two cosmic forces: the immense gravitational pull of the black hole, which tries to pull in as much matter as possible, and the radiation pressure from the accretion disk, which pushes outwards, opposing this gravitational pull. The Eddington limit represents the point at which these two forces are in balance. When the inflow of material exceeds this threshold, the radiation pressure from the accretion disk can actually push away any further infalling material, preventing the black hole from growing faster than this rate. This delicate balance plays a critical role in regulating how quasars shine. If the accretion rate exceeds the Eddington limit, the excess radiation can actually have a negative feedback effect on the accretion process. In this sense, the Eddington limit doesn't just regulate the growth of black holes, it also serves as a feedback mechanism that stabilizes their luminosity. This phenomenon is crucial for understanding how supermassive black holes in the centers of galaxies can become so luminous, yet not grow uncontrollably. We can extend this idea to understand the relationship between black holes and galaxy evolution. The radiation emitted by quasars is so powerful that it can even influence the surrounding environment, particularly in the case of active galactic nuclei, AGNs. AGNs, where the central black hole is actively accreting material, can emit vast amounts of radiation and energetic particles, which can heat up and expel the gas and dust surrounding the black hole. This process, known as feedback, is thought to play a crucial role in the regulation of star formation in the galaxy. Essentially, the energy produced by the black hole, regulated by the Eddington limit, can prevent the surrounding gas from cooling enough to form new stars, thus halting or slowing down star formation in the galaxy. In this way, the growth of supermassive black holes is intimately tied to the evolution of their host galaxies, and the Eddington limit serves as a critical piece of this puzzle. Interestingly, the Eddington limit is not just a concept that applies to stars and black holes. It also has implications for the way we think about the behavior of cosmic structures on the largest scales. One of the most intriguing aspects of the Eddington limit is how it can help explain the apparent luminosity of certain cosmic phenomena. For instance, in the case of supernovae, radiation pressure plays a role in regulating the explosion dynamics, limiting the amount of energy that can be released in a single burst. By understanding how the Eddington limit applies to the dynamics of stellar explosions, scientists can gain valuable insight into the final stages of stellar evolution and the formation of elements. This principle also informs our understanding of neutron stars, which are remnants of massive stars that have undergone supernova explosions. Neutron stars are incredibly dense objects, and their formation involves complex processes where radiation pressure from the intense heat of the collapsing core interacts with gravity in highly dynamic ways. The Eddington limit, although applied in a slightly different manner here, helps to regulate the accretion of material onto the neutron star, which is crucial for determining how these objects evolve over time. In a broader sense, the Eddington limit forces us to consider the limits of growth and consumption in the universe. Whether we're talking about a single star reaching the limit of its size or a black hole attempting to accrete more matter than it can handle, this boundary underscores the dynamic balance between forces in the universe. Gravity seeks to pull matter inward, while radiation pressure pushes outward. The tension between these two forces defines much of the behavior of cosmic objects, from stars to black holes, and plays a role in the way galaxies and larger cosmic structures evolve. One of the key aspects of this tension is the time scale over which these processes play out. While the Eddington limit is a well-defined concept in the theoretical sense, real astrophysical systems are constantly evolving. A star or black hole may momentarily exceed this limit, only to adjust as the radiation pressure increases. These systems are not static but rather in constant motion, with fluctuations in the radiation environment and material inflows that can push them closer to or further away from the limit. The result is a dynamic cosmic environment where forces are constantly at odds, creating a cosmic feedback loop that governs the birth, growth, and death of stars, black holes, and galaxies. As we continue to observe and analyze the universe, it's clear that the Eddington limit will remain an essential piece of the cosmic puzzle. It offers us a way to understand the complex interactions between radiation and gravity, two of the most fundamental forces in the universe. And as our tools for observing the universe become more advanced, we will likely uncover even more examples of how this boundary shapes the cosmos, from distant galaxies to the most extreme environments near black holes. The future of astrophysics, particularly in the context of high-energy phenomena, will undoubtedly involve more refined measurements of the Eddington limit and its role in regulating cosmic processes. New telescopes, new methods of observing gravitational waves, and the continued advancement of computational models will provide us with increasingly detailed insights into the interplay of radiation and gravity, allowing us to refine our understanding of the Eddington limit and its importance in the grand cosmic scheme. The study of the Eddington limit is not just a matter of theoretical curiosity. It is central to understanding the dynamic and ever-evolving nature of the universe itself. As we continue to study the stars, black holes, and galaxies, this concept will remain a key guiding principle, helping us unlock the mysteries of how the universe behaves on its largest scales. As we further explore the significance of the Eddington limit in the grand structure of the universe, it becomes evident that this concept is not just a theoretical curiosity, but a crucial element in understanding the evolution of the cosmos. From the earliest moments of star formation to the complex dynamics of black holes at the centers of galaxies, the Eddington limit is a guiding force in the regulation of cosmic matter. It's a tool that allows astrophysicists to predict the behavior of stars and black holes, providing us with a deeper understanding of how the universe operates on the largest scales. To truly appreciate the significance of the Eddington limit, let's take a closer look at its implications for the life cycle of stars. The life of a star is a delicate balance between gravity, which pulls matter inward, and the radiation pressure generated by nuclear fusion, which pushes outward. The Eddington limit plays a crucial role in regulating this balance, determining how much mass a star can contain before the outward pressure from radiation becomes too great for gravity to hold it together. When a star reaches the end of its life, it undergoes dramatic changes that can result in the creation of some of the most exotic objects in the universe. Supernovae, which occur when massive stars explode, are among the most intense phenomena in the cosmos. These explosions release an enormous amount of energy, and the radiation pressure from this energy can temporarily exceed the gravitational pull of the star's core, driving away material that would otherwise collapse into a black hole. The Eddington limit helps explain why some supernovae don't collapse into black holes immediately, instead undergoing a phase of outward radiation that pushes away the infalling material. Interestingly, the Eddington limit is not just a limiting factor for stars but also for the formation of black holes themselves. In the case of stellar mass black holes, the intense radiation pressure from the accretion disk can prevent matter from falling in too quickly, regulating the rate at which the black hole can grow. This means that, even in the most extreme environments near black holes, there is a feedback loop that prevents them from consuming all the material around them. The Eddington limit is essentially the speed limit for black holes, a limit beyond which they cannot grow indefinitely, no matter how much material is available. The concept of radiation pressure, as governed by the Eddington limit, also extends to larger cosmic structures, such as galactic centers. Supermassive black holes, which reside at the hearts of most galaxies, can generate immense amounts of radiation as they pull in material from their surroundings. This radiation, as in the case of quasars, can have a profound effect on the galaxy itself. When a black hole accretes material at a rate that exceeds the Eddington limit, the radiation pressure can exert significant influence on the surrounding gas, halting or even reversing the process of star formation. This feedback effect is one of the ways in which the growth of supermassive black holes is tied to the evolution of their host galaxies, providing a link between the smallest and largest structures in the universe. In fact, the study of the Eddington limit can help us understand not just how individual stars and black holes behave, but also how galaxies form and evolve over cosmic timescales. The radiation pressure from quasars and other active galactic nuclei can clear out gas from the centers of galaxies, preventing the formation of new stars and shaping the overall structure of the galaxy. This process, known as feedback, is thought to be one of the key drivers of galaxy evolution, as it regulates the amount of gas available for star formation and helps to explain why some galaxies seem to turn off star formation after a period of rapid growth. In terms of the future of our understanding of the Eddington limit, ongoing advancements in observational technology are likely to provide new insights into its role in the universe. For example, the next generation of space telescopes, such as the James Webb Space Telescope, will allow us to observe distant galaxies and black holes in unprecedented detail. These observations will enable astrophysicists to refine our understanding of the Eddington limit, shedding light on how it influences the formation and evolution of galaxies, stars, and black holes. Additionally, the study of gravitational waves, which can provide direct evidence of black hole mergers, may offer new insights into the limits of black hole growth and the role of radiation pressure in regulating this growth. One of the most fascinating aspects of the Eddington limit is how it links the behavior of individual objects, like stars and black holes, to the larger-scale processes that govern the evolution of the universe. The interplay between radiation and gravity is at the heart of many of the most intriguing phenomena in astrophysics, from the formation of stars to the evolution of galaxies and the growth of supermassive black holes. The Eddington limit provides a framework for understanding how these forces balance each other, shaping the cosmic landscape in ways that are still being explored. As we continue to study the universe, the Eddington limit will undoubtedly remain a central concept in our quest to understand the most fundamental processes that drive the cosmos. Its impact reaches far beyond the individual objects we observe in the sky, extending to the very structure of the universe itself. By exploring the delicate balance between radiation and gravity, we can gain new insights into the forces that shape our universe, from the birth of stars to the growth of galaxies and the formation of black holes. The Eddington limit is more than just a scientific curiosity. It's a key that unlocks many of the mysteries of the cosmos. The next frontier of research lies in understanding how this balance works in the most extreme environments in the universe. As we push our observational capabilities to new heights, we may uncover entirely new phenomena that challenge our understanding of the Eddington limit. For example, what happens when a black hole or a star exceeds the limit in ways we've never observed before? Could there be regions of the universe where radiation pressure and gravity operate in completely unexpected ways? These are questions that will drive future research in astrophysics, and the answers could reveal new layers of complexity in the universe. Moreover, as we continue to study the Eddington limit, we may find that this concept is connected to even more exotic ideas in theoretical physics, such as quantum gravity and the behavior of spacetime in the presence of extreme forces. The Eddington limit might not just be a concept that governs radiation and gravity. It could be a clue to understanding how the very fabric of the universe behaves at the most fundamental level. Perhaps, in the future, we'll discover that the Eddington limit is part of a larger set of cosmic laws that govern everything from the smallest particles to the largest structures in the universe. For now, we can marvel at the beauty and complexity of the Eddington limit. It's a concept that ties together radiation, gravity, and the growth of cosmic objects in ways that are still being unraveled. Whether it's regulating the size of stars, controlling the growth of black holes, or influencing the evolution of galaxies, the Eddington limit is a fundamental force in the cosmos, shaping the universe as we know it. And as we continue to explore the vast expanse of space, we will undoubtedly uncover even more secrets hidden within this seemingly simple yet profoundly important concept. The more we delve into the cosmic mysteries surrounding the Eddington limit, the more it becomes clear that this boundary represents a delicate equilibrium in the universe. Beyond being a tool for understanding the behavior of stars and black holes, the Eddington limit provides insights into the fundamental forces that govern the cosmos at both the largest and smallest scales. It highlights the intricate dance between the inward pull of gravity and the outward push of radiation pressure. This dynamic relationship is crucial for astrophysics, offering clues about the nature of matter, energy, and even the fabric of spacetime itself. One fascinating aspect of the Eddington limit is its implications for the formation and evolution of stars. During the early stages of a star's life, nuclear fusion in its core generates enormous amounts of energy. This energy, in the form of light and other types of radiation, creates an outward pressure that pushes against the gravitational force trying to pull everything inward. If a star becomes too massive, the radiation pressure can exceed the gravitational pull, which can disrupt the star's ability to maintain equilibrium. The Eddington limit serves as the threshold beyond which a star can no longer maintain a stable size and would lose mass in the form of intense radiation, ultimately preventing it from growing any larger. As a star nears this limit, the outward pressure of radiation becomes stronger and more significant in shaping its behavior. For example, in massive stars, this can lead to an increased rate of mass loss. These stars expel material into space through powerful stellar winds, which are driven by the immense radiation pressure. In some cases, the energy produced in a star's core can be so intense that it forces the star to shed large amounts of matter into the surrounding space, preventing it from collapsing further into a black hole. This massive loss of mass plays a crucial role in determining the eventual fate of the star. However, the Eddington limit's influence is not limited to stars alone. Black holes, those enigmatic objects that possess gravity so powerful that not even light can escape, are also affected by this radiation pressure threshold. In fact, the Eddington limit provides a key to understanding how black holes grow and interact with their surroundings. As matter falls into a black hole, it forms an accretion disk that heats up due to friction, emitting intense radiation. If the rate at which material is accreting exceeds the Eddington limit, the radiation pressure generated by the accretion disk can push against the inflowing matter, halting further growth. This feedback mechanism acts as a form of regulation, preventing black holes from growing uncontrollably. Interestingly, this radiation pressure plays a significant role in the growth of supermassive black holes, which reside at the centers of most galaxies. Supermassive black holes, which can contain millions to billions of times the mass of the Sun, can exert such intense radiation pressure that they influence the very structure of their host galaxies. The radiation from a supermassive black hole can have far-reaching effects on its surroundings, heating up gas and even preventing the formation of new stars. This process, known as feedback, has profound implications for the evolution of galaxies. It suggests that black holes and their surrounding environments are intricately connected, with the growth of black holes being regulated by the radiation pressure they produce. What is particularly intriguing about this process is how it links the evolution of galaxies to the growth of supermassive black holes. In many cases, the activity of a supermassive black hole can have a direct impact on the star formation rates within its host galaxy. When a black hole accretes matter at an extremely high rate, the radiation pressure generated can blow away the surrounding gas, effectively halting star formation. This feedback mechanism can prevent the galaxy from forming new stars and limit the amount of gas available for future stellar birth. In some cases, this feedback loop may even cause galaxies to enter a phase known as quenching, in which the rate of star formation dramatically decreases or stops altogether. This has been observed in certain galaxies, where the central supermassive black hole has reached a point of maturity, and its radiation pressure has essentially shut down the star formation process. As a result, the galaxy evolves into what is known as a red and dead galaxy, one that has exhausted its supply of gas for star formation and is no longer producing new stars. The study of the Eddington limit also opens up exciting possibilities for understanding the interplay between radiation and gravity on even more extreme scales. For instance, in the case of massive black holes at the centers of galaxies, this feedback mechanism may influence the growth of large-scale cosmic structures. The radiation pressure exerted by these supermassive black holes can affect the surrounding gas, regulating the formation of stars and even shaping the overall structure of the galaxy. This suggests that the Eddington limit is not just a local phenomenon but a universal one, with the potential to influence the evolution of entire galaxies over cosmic timescales. Moreover, as we look further into the universe, the Eddington limit may also help us understand the behavior of exotic objects like quasars and active galactic nuclei. These extremely bright objects are powered by the intense radiation produced by the accretion of matter into a supermassive black hole. The radiation emitted by these objects can be so intense that it reaches the Eddington limit and exerts pressure on the surrounding material, preventing further accretion. This feedback mechanism plays a crucial role in regulating the growth of these objects and shaping the environment around them. The Eddington limit is also relevant in the context of star formation in the early universe. During the formation of the first stars, often referred to as population 3 stars, the intense radiation generated by these massive objects could have contributed to the reionization of the universe. This process involved the ionization of neutral hydrogen atoms, making the universe more transparent to light. The radiation pressure from these first-generation stars may have played a role in shaping the conditions necessary for the formation of galaxies and larger cosmic structures. As our understanding of the Eddington limit continues to evolve, so too will our appreciation for its profound impact on the universe. With the advent of new observational techniques, such as the upcoming James Webb Space Telescope, we are poised to gain unprecedented insights into the behavior of distant stars, black holes, and galaxies. These observations will provide new data that will allow astrophysicists to refine our understanding of the Eddington limit and its role in shaping the cosmos. With this knowledge, we can continue to piece together the puzzle of the universe's formation and evolution, unlocking the secrets of how matter, energy, and gravity interact on the grandest scales. The Eddington limit is far more than a theoretical construct. It is a fundamental principle that governs the behavior of stars, black holes, and galaxies. It is a delicate balance between radiation pressure and gravitational pull that regulates how matter behaves in the most extreme environments of the universe. From the formation of stars to the growth of supermassive black holes, the Eddington limit plays a crucial role in shaping the structure and evolution of the cosmos. As we continue to explore the universe, we will undoubtedly uncover even more mysteries hidden within this concept, further deepening our understanding of the forces that shape the very fabric of space-time. The Eddington limit is a cosmic regulator, guiding the formation and evolution of the universe's most fundamental objects and providing us with a deeper understanding of the universe's grand design. As we continue our exploration of the Eddington limit, we begin to uncover its profound influence on both stellar and galactic scales, shaping the evolution of the universe in subtle but crucial ways. While we have discussed how this limit acts as a governing force for the growth and behavior of stars and black holes, its consequences stretch far beyond these cosmic entities. In fact, the Eddington limit plays a key role in the overall balance of the universe, impacting everything from the dynamics of gas clouds to the formation of galaxies and clusters of galaxies. One critical aspect of the Eddington limit that demands attention is its effect on the formation of stars in the early universe. During the epoch of the first stars, which occurred around 200 to 400 million years after the Big Bang, the universe was filled with a dense fog of neutral hydrogen gas. These early stars, often referred to as population 3 stars, were much more massive than those in the present-day universe. Due to their size, they generated tremendous amounts of radiation that could influence the surrounding gas. As these early stars began to shine, their radiation pressure played a role in regulating how gas could collapse to form new stars. The radiation from population 3 stars could have been intense enough to push against the surrounding gas, preventing it from further collapsing under its own gravity. This process, known as radiative feedback, was vital in the formation of the first galaxies. The radiation pressure could have effectively halted the collapse of gas clouds before they could form new stars, shaping the early stages of galaxy formation. By regulating the rate at which gas clouds could collapse, the Eddington limit helped determine the sizes and structures of the first galaxies. In essence, this feedback mechanism ensured that the early universe's star formation was not too rapid or chaotic, allowing for the delicate balance necessary for the emergence of galaxies as we know them today. As we move forward in time, the Eddington limit continues to influence the development of galaxies in more nuanced ways. In the context of more mature galaxies, the radiation pressure generated by a supermassive black hole at the center of a galaxy can act as a regulator, controlling the rate of star formation in the surrounding galaxy. In galaxies with active supermassive black holes, known as active galactic nuclei (AGN), the intense radiation produced by matter falling into the black hole can heat up the surrounding gas, preventing it from cooling down and collapsing to form new stars. This phenomenon, known as AGN feedback, can play a significant role in quenching star formation in a galaxy, ultimately altering its evolutionary path. The interplay between the Eddington limit and supermassive black holes also highlights the connection between radiation pressure and the large-scale structure of the universe. In the most massive galaxies, supermassive black holes can influence the dynamics of the entire galaxy cluster. The radiation pressure from these black holes can push gas out of the cluster, preventing the formation of new stars and reducing the amount of cold gas available for future star formation. This feedback loop is particularly evident in the giant elliptical galaxies that populate the centers of galaxy clusters. These galaxies, which are largely devoid of young stars, are thought to have undergone a period of intense AGN activity, during which their central supermassive black holes expelled vast amounts of gas, effectively shutting down star formation in the galaxy. Interestingly, the Eddington limit is not only relevant to the present-day universe but also provides valuable insight into the evolution of the early cosmos. The process of reionization, which occurred around 400 million years after the Big Bang, was driven by the intense radiation produced by the first stars and black holes. As these early cosmic objects began to emit light, their radiation ionized the surrounding hydrogen gas, making the universe more transparent to light. This process had profound implications for the formation of galaxies, as the ionized regions created by radiation pressure facilitated the cooling and collapse of gas into dense clouds, where stars and galaxies could form. The interplay between radiation pressure and gravitational collapse during the reionization epoch is a key aspect of the early universe's evolution. Without the regulation provided by the Eddington limit, the universe may have experienced an overabundance of radiation, which could have stifled star formation and delayed the onset of galaxy formation. Instead, the Eddington limit acted as a natural brake on the growth of the first cosmic objects, ensuring that the universe's early development was either too slow nor too rapid. Even in modern times, the study of the Eddington limit continues to provide astrophysicists with critical insights into the behavior of exotic objects like quasars. Quasars are extremely bright objects powered by the accretion of matter into supermassive black holes, and their brightness can exceed that of entire galaxies. However, as the accretion rate increases, so too does the radiation pressure. When a quasar's radiation exceeds the Eddington limit, the radiation pressure can halt further accretion, preventing the quasar from becoming even brighter. This is an example of how the Eddington limit helps to regulate the growth of some of the most extreme objects in the universe, ensuring that their energy output remains within a certain range. This regulation is particularly important in the context of black hole growth. If a black hole were able to accrete matter at an uncontrollable rate, it could potentially grow so large that it would begin to disrupt the fabric of spacetime itself. However, the Eddington limit serves as a natural safeguard against this possibility. By regulating the rate at which matter can fall into a black hole, it ensures that even the most massive black holes grow at a manageable pace. This delicate balance between gravity and radiation pressure is what keeps the universe in check, allowing for the orderly growth and evolution of cosmic structures. As we move forward in the study of astrophysics, the Eddington limit will continue to be a cornerstone of our understanding of the universe. New technologies, such as the James Webb Space Telescope, are allowing scientists to peer deeper into the cosmos than ever before, uncovering previously unseen objects and phenomena. These observations will provide new insights into the behavior of stars, black holes, and galaxies, helping us refine our understanding of how the Eddington limit shapes the universe. In the future, as we explore more distant regions of space, we may discover even more extreme environments where the Eddington limit plays a crucial role. The study of distant galaxies, especially those in the early stages of formation, will provide valuable clues about how the balance between radiation pressure and gravity influences the growth of these galaxies. By examining the feedback mechanisms at play in these distant systems, we can gain a deeper understanding of how the Eddington limit operates across cosmic time scales. The Eddington limit is a fundamental concept in astrophysics that governs the behavior of stars, black holes, and galaxies. By balancing the forces of gravity and radiation pressure, it regulates how much matter can be consumed by stars and black holes, shaping the evolution of the universe. From the formation of the first stars to the growth of supermassive black holes, the Eddington limit plays a crucial role in the development of the cosmos. As we continue to explore the universe, the insights gained from studying this cosmic boundary will deepen our understanding of the forces that govern the very fabric of space and time. The Eddington limit, while a central concept in the study of stars and black holes, extends its influence across many different scales and realms of astrophysics, affecting the way we observe and interpret the universe. One of the areas where its impact is particularly evident is in the behavior and structure of galaxy clusters, which are vast collections of galaxies bound together by gravity. Understanding the role of the Eddington limit in these clusters provides essential insights into their formation, dynamics, and evolution. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of galaxies, along with vast amounts of hot gas and dark matter. The distribution of matter in these clusters is not uniform, with the central regions being much denser than the outskirts. At the heart of many galaxy clusters, supermassive black holes reside in the centers of the dominant galaxies, generating intense radiation from the matter being drawn into them. As these black holes grow, their radiation can have profound effects on the cluster's gas dynamics, and the Eddington limit plays a key role in regulating this process. The radiation pressure produced by supermassive black holes in galaxy clusters can prevent the surrounding gas from cooling and collapsing to form new stars. This phenomenon is particularly evident in so-called cooling flow clusters, where the central gas is relatively cool compared to the surrounding environment. In the absence of any external feedback mechanisms, this cool gas would slowly fall into the central supermassive black hole, leading to a gradual decrease in the gas supply and an increase in the temperature of the surrounding gas. However, as the black hole continues to accrete matter, the Eddington limit acts as a natural regulator, preventing the black hole from growing too rapidly and emitting excessive amounts of radiation that could disrupt the gas dynamics of the cluster. One interesting example of this phenomenon is the feedback mechanism observed in the cores of galaxy clusters. In many clusters, the supermassive black holes at their centers undergo cycles of growth and quenching, driven in part by the Eddington limit. During periods of rapid accretion, the black holes emit vast amounts of radiation, which can push gas away from the center of the cluster, effectively shutting down star formation in that region. However, as the black hole's accretion slows, the gas can cool and fall back toward the center, leading to a new cycle of accretion and radiation. This process helps regulate the growth of both the black hole and the galaxy cluster, maintaining a delicate balance between radiation pressure and gravitational collapse. Interestingly, this feedback process is not limited to galaxy clusters but is also observed in individual galaxies. The presence of an active galactic nucleus, AGN, in a galaxy can significantly influence the evolution of the galaxy by regulating the amount of gas available for star formation. AGN feedback can prevent the formation of new stars by heating the surrounding gas, making it too hot to collapse under gravity. This process can ultimately lead to a red and dead galaxy, where star formation ceases and the galaxy becomes dominated by older stars. The Eddington limit, by controlling the rate at which matter can accrete onto a black hole, plays a crucial role in determining the timescale over which this process occurs. As we look deeper into the cosmos, the Eddington limit helps explain the observed diversity in galaxy types and their evolutionary paths. While some galaxies, particularly those in dense clusters, experience prolonged periods of quiescence due to AGN feedback, others, such as spiral galaxies, continue to form new stars at a steady rate. The balance between radiation pressure and gravity, as governed by the Eddington limit, plays a central role in determining the fate of these galaxies, influencing their size, structure, and star formation rates over cosmic time scales. In addition to its influence on the large-scale structure of the universe, the Eddington limit also plays a crucial role in the study of exotic objects like white dwarfs and neutron stars. These compact remnants of stars, which are the end states of low and medium mass stars, respectively, are subject to the delicate balance between radiation pressure and gravity. In the case of white dwarfs, the Eddington limit sets a strict upper bound on their mass, known as the Chandrasekhar limit. If a white dwarf exceeds this limit, its gravity becomes too strong for the electron degeneracy pressure, the force that supports the white dwarf against collapse, to counteract, leading to a catastrophic collapse that can result in a supernova explosion. This process, which marks the death of a white dwarf, is one of the most powerful events in the universe, releasing immense amounts of energy in the form of light and radiation. Similarly, neutron stars, the remnants of more massive stars, are also subject to the effects of the Eddington limit. These ultra-dense objects are held up by neutron degeneracy pressure, which counteracts the force of gravity. However, if a neutron star exceeds a certain mass, known as the Tolman, Oppenheimer, Volkoff, TOV limit, the gravitational pull becomes too strong for neutron degeneracy pressure to support the star, leading to its collapse into a black hole. The Eddington limit is not directly involved in this collapse, but it sets a fundamental limit on the amount of matter that can be accreted by the neutron star before the balance between radiation pressure and gravity is disrupted. The Eddington limit's influence is also felt in the study of cosmic phenomena like gamma-ray bursts, GRBs, which are some of the most energetic events in the universe. These bursts, which are thought to be caused by the collapse of massive stars or the merging of compact objects like neutron stars, release enormous amounts of energy in the form of high-energy radiation. The radiation from a GRB can exceed the Eddington limit, leading to the formation of shock waves and the ejection of material from the central object. These shock waves can interact with the surrounding gas, producing the characteristic afterglows that we observe in the aftermath of a GRB. Interestingly, the Eddington limit has also been proposed as a possible explanation for the formation of certain types of cosmic structures. For example, it has been suggested that the formation of massive black holes in the centers of galaxies may be regulated by the Eddington limit. As matter falls toward the black hole, the radiation pressure generated by the accretion process would eventually reach a point where it prevents further accretion. This feedback mechanism could explain the observed correlation between the mass of a supermassive black hole and the properties of its host galaxy. By regulating the growth of these black holes, the Eddington limit may play a key role in determining the relationship between galaxies and their central black holes. In recent years, astronomers have been able to directly observe the effects of the Eddington limit in various regions of the universe. Observations of distant galaxies and quasars have provided new insights into how radiation pressure regulates the growth of black holes and the formation of galaxies. For example, the discovery of extremely massive black holes at the centers of high redshift galaxies has led to questions about how these black holes grew so quickly in the early universe. Some scientists believe that the Eddington limit may have played a crucial role in limiting the growth of these black holes, allowing them to reach their enormous sizes without emitting excessive radiation that would have disrupted their accretion. As we continue to explore the universe, the Eddington limit will undoubtedly remain a key concept in our understanding of the cosmos. New technologies, such as the next generation of space telescopes, will allow us to study the effects of radiation pressure and gravitational forces in greater detail, shedding light on the complex interactions that govern the behavior of stars, black holes, and galaxies. By understanding the delicate balance between radiation and gravity, we can gain deeper insights into the fundamental forces that shape the universe and the processes that govern its evolution over cosmic time scales. The Eddington limit is a fundamental concept in astrophysics, influencing the behavior and evolution of stars, black holes, galaxies, and even the large-scale structure of the universe. From the formation of the first stars to the growth of supermassive black holes and the dynamics of galaxy clusters, the Eddington limit plays a crucial role in shaping the universe as we know it. By regulating the rate at which matter can be consumed by these cosmic objects, the Eddington limit ensures a delicate balance between radiation pressure and gravity, allowing the universe to evolve in an orderly and predictable manner. As our understanding of the universe deepens, the Eddington limit will continue to be a key piece of the puzzle, helping us unlock the mysteries of the cosmos and the forces that govern its behavior. The implications of the Eddington limit stretch far beyond the individual scales of stars and black holes. As we continue to investigate the vast and complex nature of the universe, it becomes clear that this limit plays a critical role in shaping larger structures and phenomena. From the origins of galaxies to the formation of black hole mergers and the physics of high-energy cosmic events, the Eddington limit offers a unique lens through which to understand the balance of forces in the cosmos. For instance, one area where the Eddington limit continues to yield fascinating insights is in the study of active galactic nuclei, AGN, where supermassive black holes reside at the centers of galaxies, feeding on surrounding gas and dust. AGNs, often observed as quasars or Seyfert galaxies, are some of the brightest objects in the universe, thanks to the intense radiation produced by accreting matter around the black hole. The Eddington limit governs the amount of material that can be funneled into these black holes without violating the balance between gravitational attraction and the outward pressure from radiation. At the heart of a quasar, matter is falling towards the supermassive black hole at an extraordinarily fast rate, generating radiation that can be millions or even billions of times more luminous than the entire host galaxy. However, this intense radiation exerts pressure on the surrounding material, effectively pushing it outward. If the radiation pressure becomes too strong relative to the gravitational pull of the black hole, it would prevent further material from falling in. This self-regulation of accretion, as dictated by the Eddington limit, helps maintain the stability of the black hole and prevents it from overfeeding or growing too rapidly. Overfeeding can lead to extreme consequences such as the ejection of vast amounts of material in the form of relativistic jets. These jets are some of the most striking phenomena in the universe, emanating from the poles of the black hole at nearly the speed of light. The balance maintained by the Eddington limit is critical in modulating the amount of material being funneled into the black hole, which in turn influences the dynamics of these jets. They can extend over millions of light years, affecting the surrounding galactic environment, including triggering star formation or quenching it entirely. These jets, in fact, provide a dramatic demonstration of the intricate relationship between radiation and gravity that governs the universe. The importance of the Eddington limit becomes even more apparent when we consider the growth patterns of galaxies and their central black holes. Recent research into the coevolution of galaxies and black holes suggests that the two are intimately linked. As a galaxy forms and its stars evolve, the activity of the central black hole plays a crucial role in regulating the galactic environment. The radiation pressure from the accreting black hole, constrained by the Eddington limit, influences the rate at which gas can condense to form new stars. In cases where the Eddington limit is exceeded, black holes can halt star formation by expelling vast amounts of gas, heating the surrounding environment to the point where further cooling and collapse become impossible. This feedback loop between black holes and galaxies helps maintain an equilibrium in which the black hole grows at a controlled pace, without rapidly exhausting the gas supply that fuels both its growth and the star formation within the host galaxy. This relationship has been found to play a significant role in the formation of so-called red and dead galaxies, which are characterized by an older stellar population and no ongoing star formation. At the same time, in galaxies with less active central black holes, the Eddington limit is not as restrictive, allowing more gas to accumulate, potentially leading to more vigorous star formation and more rapid evolution. In this way, the Eddington limit offers a framework to explain why different galaxies evolve along different paths and at different rates, depending on the amount of radiation pressure being exerted by their central black holes. The Eddington limit also has crucial implications for the study of gamma-ray bursts, GRBs, one of the most energetic events in the universe. GRBs are typically associated with the collapse of massive stars or the merger of compact objects like neutron stars or black holes. These violent events can release as much energy in a few seconds as the Sun will emit over its entire 10 billion-year lifetime. The energy from a GRB can exceed the Eddington limit of the collapsing star, leading to a release of radiation that produces shock waves and material ejections, resulting in the characteristic gamma-ray afterglows that we observe. The role of the Eddington limit in these catastrophic events underscores the importance of radiation pressure in controlling the dynamics of collapsing stars and the subsequent formation of black holes. While the radiation pressure from a GRB can momentarily overpower the gravitational pull of the collapsing star, it is the balance between these forces that dictates the precise conditions under which such violent events can occur. By regulating how much radiation can escape and how much matter can fall in, the Eddington limit essentially sets the stage for the eventual formation of a black hole and the accompanying gamma-ray burst. Similarly, the study of black hole mergers has revealed that the Eddington limit influences the growth and eventual merger of black holes and binary systems. When two black holes orbit each other and eventually merge, the process is often accompanied by the release of gravitational waves, ripples in spacetime that propagate outward at the speed of light. The release of energy during these mergers can be immense, and understanding how the Eddington limit affects the accretion of matter during this process provides valuable insights into the physics of these high-energy cosmic events. For example, as matter is drawn toward a black hole in a binary system, the rate of accretion is often governed by the Eddington limit, which ensures that the black hole cannot accrete matter too quickly. If the accretion exceeds this limit, the black hole would be unable to handle the massive radiation output, and the system would stabilize to prevent further material from being drawn in. This balance is not only crucial for understanding the merger process, but also provides a key piece of the puzzle in our search for gravitational waves, offering insights into the complex dynamics of black hole binaries and their eventual mergers. In addition to these large-scale phenomena, the Eddington limit also governs the behavior of compact objects like white dwarfs and neutron stars. As previously mentioned, the Eddington limit places strict limits on the mass of white dwarfs, with the Chandrasekhar limit providing the upper mass threshold before gravitational collapse leads to a supernova explosion. In the case of neutron stars, the Eddington limit helps regulate how much matter can be accreted before the star becomes unstable and collapses into a black hole. This delicate balance between radiation pressure and gravity ensures that the universe remains in a constant state of dynamic equilibrium, where the formation and death of stars, the creation and consumption of matter by black holes, and the evolution of galaxies are all intertwined in a grand cosmic dance. This cosmic balance, regulated by the Eddington limit, is not just a theoretical concept but a practical tool for understanding the universe at both the small and large scale. It provides essential insights into the behavior of stars and black holes, the formation of galaxies, and the evolution of the universe itself. By continuing to study the Eddington limit and its implications, astronomers can unlock new mysteries about the nature of matter, radiation, and gravity. As we push the boundaries of space exploration and observational technology, the Eddington limit will undoubtedly remain a cornerstone in our understanding of the cosmos, guiding us toward new discoveries and deeper insights into the fundamental forces that govern our universe. In the grand scheme of things, the Eddington limit represents more than just a theoretical limit. It symbolizes the delicate interplay of forces that keeps the universe in balance. By regulating the way matter is consumed by stars and black holes, this limit ensures that the cosmos remains in a state of dynamic evolution. When new stars are born, black holes grow, and galaxies evolve in an ongoing cycle that has lasted for billions of years. In the end, it is the Eddington limit that ensures the universe maintains its perfect balance, preventing runaway processes and keeping the cosmic order intact. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.